our participants hailing from different time zones around the world. I'm Shinjan, a member of the Geological Institute of the Department of Geology, Presidency University, Kolkata, and I shall be your host for the day. So, first, I would request everyone to keep their cameras and microphones off throughout the lecture, as this is extremely essential to maintain a smooth session. A question answer form has already been sent to all the participants via mail and telegram groups, along with the shared webinar link. In case you do not find it in your inbox, kindly check your spam folder. If you're viewing us on YouTube, then please check the description box to find the attached link for the question answer form. On behalf of the Geological Institute, Presidency University, Kolkata, I would like to welcome you all to the sixth lecture session of GEOCHRON 2020. Today, we are really fortunate to have with us Professor Ian Fitzsimmons, head of the School of Earth and Planetary Sciences, whose teaching spans theoretical aspects of metamorphic petrology and geochemistry to ore deposits and mineral exploration, global tectonics, and geological history of the continents. Professor Fitzsimmons has gained fame all around the globe for his particular expertise in the use of thermodynamic and mineral chemical data in the estimation of pressure temperature histories for crustal and mantle rocks, the uranium-lead isotope geochronology of accessory minerals, the use of detrital zircon H spectra in lithological and tectonic correlations, and many more. Professor Fitzsimmons is a fellow of the Geological Society of London, fellow of the Mineralogical Society, and also a member of the Geological Society of Australia. His research work and utmost dedication towards the profession of teaching has made him the recipient of several awards like Mackay Medal of Mineralogical Society of Great Britain and Ireland, Faculty of Science and Engineering Citation for Outstanding Contribution to Student Learning, F. L. Stilwell Award of the Geological Society of Australia, to name a few. We are highly honored to have him with us delivering a talk on the aforementioned topic. We are sure that the lecture session will be enriching and a great experience for us all. I would now request our very own Professor Shankar Bose, professor in the Department of Geology, Presidency University, to give a bit more introduction about our speaker and to welcome him to start the session.
Thank you, Shinjin. It's a very good morning and good afternoon to all the people. Let me introduce our beloved Professor Ian Fitzsimmons. Professor Ian Fitzsimmons is working at the Curtin University, Australia since 1998. He grew up in the United Kingdom and studied at Cambridge and Oxford universities before completing a PhD at the University of Edinburgh and research fellowships at the University of London and Monash University in Melbourne. His research provided significant understanding of the evolution of East Antarctica and other parts of the ancient Gondwana supercontinent. His pioneering work on the Preeds Bay area remains a profound motivation for researchers in Antarctica over the next few decades. He participated in 4 expeditions to Antarctica and multiple field trips in India, Madagascar, Africa, and Australia. Professor Fitzsimmons has taught and mentored more than 1,000 students over the last 20 years, giving classes on introductory geology, field geology, metamorphism, and mineral deposits, and winning multiple teaching awards. He is a former acting director of the Western Australian School of Mines and has been the head of Curtin School of Earth and Planetary Sciences since 2018. With a responsibility of about 100 staffs, 500 undergraduate students and 200 postgraduate students in the earth, marine, planetary, and geospatial sciences. He remains a role model for many budding geoscientists for years. Apart from all this, he is an excellent communicator of geoscience, and I'm sure all of us will enjoy his talk today. With this brief introduction, I will request Ian to come to the stage and deliver his talk. Thank you.
Thank you very much, Professor Bose, for that very kind introduction. And hello to everyone who's watching this presentation. Wherever you are, I hope that you're all safe and well. I've had a quick glance down some of the names, and I see there's at least one person from my own institute watching. So hello, Aaron. I've also heard that perhaps Professor Shaibal Gupta is watching from Kharagpur. I'd like to say a special hello to him. And hello to all of you. As you've heard, I'm speaking to you from Perth in Western Australia. Perth's often described as one of the most isolated cities in the world. And after several months of being even more isolated than usual, it's a wonderful opportunity to have here to be able to connect with all of you today. As Professor Bose said, I've only been in Western Australia for about 20 years or so, and I should acknowledge that although I call this place Perth, in fact it's I'm speaking to you from the traditional lands of the Whadjuk Noongar people who've looked after this country for tens of thousands of years. And I should acknowledge their elders and what they've done to look after this land in the past and will continue to do so in the future. So I'll be talking to you today about metamorphism, in particular the topic of how the continental crust can get really hot. So I'm talking about heat and how it produces metamorphism. We're all familiar with heat being perhaps the most obvious driver of metamorphic processes. Perhaps the simplest example is in a contact aureole adjacent to an igneous pluton. But in fact, heat is one of the most difficult metamorphic drivers to predict and understand in any quantitative way. And this is because it doesn't behave in a simple way. We measure heat commonly by the temperature of a material, but different materials heat up different amounts for the same amount of heat. We measure that in terms of heat capacity. Materials their temperature can change by different amounts depending on latent heat. If they undergo a reaction, that can draw in heat or give out heat. But perhaps the most complicating factor is that it takes time for rocks to heat up. This is because geological materials do not conduct heat very quickly, very easily. So we always have to consider the variable of time. And this makes understanding heat really quite difficult. And in fact, often to reach any quantitative conclusions on heating in metamorphic origins, we need to construct models, mathematical models that predicts how the temperature will change as we alter various variables. And I'll talk a little bit about that later on in my talk. So I think it's probably best that I move to my PowerPoint show. Hopefully you can all see this presentation. So as I said, the title of my talk is How Does Continental Crust Get Really Hot? And in the background there you can see a map of India. This is quite an old map produced by Louis Fermor when he was a director of the Geological Society of India in 1936, and I'll return to this map a little bit later in my talk. But India is in fact a wonderful place to try and understand why the continental crust gets really hot. And as I said, I'll return to that in a little while. I want to start just with some acknowledgements. Firstly, to the Geological Institute at the Presidency University for inviting me to give this presentation. I should acknowledge my collaborators on high temperature metamorphism, which is a very long list, but I've given 3 names there. Chris Clark, who is one of my colleagues here at Curtin, in Australia, Simon Harley at the University of Edinburgh, who was actually supervised my PhD many years ago, and Dave Healy, who's based at the University of Aberdeen. He has quite a lot of mathematical expertise, and he's helped us construct some numerical models of metamorphism. And I've mentioned those three in particular because they were co-authors on a paper that we published in 2011, and I'll be talking a little bit about some of the results presented in that paper today. Given that many of the audience will be based in India, I should acknowledge the various colleagues who've assisted me over the years with my fieldwork in India. I've listed 5 there in alphabetical order. Dr. Chetty, who first introduced me to the southern granulite terrain a long time ago. Professors Baumik and Gupta, who at the Indian Institute of Technology at Kharagpur, who've assisted my fieldwork in the Eastern Ghats, and Professors Santosh and Dr. Shaji, who've assisted me in the southern granulite terrain. And I should also acknowledge that much of the work I've conducted has been funded by the Australian Research Council. So, I'm talking about thermal regimes in the continental crust. We all know that metamorphic rocks have a wide range of pressure temperature values, and we often represent those in terms of the metamorphic facies, and you can see those represented on this diagram here, this plot of pressure against temperature, and you'll be familiar with the names of these various facies: the green schist facies, the amphibolite facies, the granulite facies, the blue schist facies, and so on. Each of these represent a different field on a pressure temperature plot like this. And we can compare these different facies, these different pressure temperature conditions, with a typical continental geotherm. So a geotherm is just it's a representation of how we believe the temperature varies with depth in the continental crust. And it's shown by this curved line here. It varies between different parts of the world, but in stable continental crust, it's typically thought to be about 15 to 20 degrees Celsius increase in temperature with every kilometre of depth. And that's that purple line on that plot there. And what we can see is that metamorphic rocks commonly preserve conditions that are quite different from that typical geotherm. Some metamorphic rocks preserve conditions that are colder than normal conditions, so they lie above and to the left of that geotherm. Higher pressures, lower temperatures. Other rocks preserve conditions that are hotter than the normal geotherm. They lie to the right and below that purple line. So they are at shallower levels in the crust or higher temperatures than that geotherm. Why is this? Well, it seems clear that the reason why many rocks preserve different, typically a stable continental crust, is because of tectonics. They reflect different tectonic settings, different transient events caused by tectonics that change the temperature and pressure of rocks in the crust. And we commonly represent this in terms of what's sometimes called the facies series, or sometimes represented in terms of pressure divided by temperature. I'll refer to it as P over T. And we talk about high P over T metamorphism or high pressure metamorphism in the field I've highlighted there. So higher pressures, lower temperatures. And we commonly recognize this type of metamorphism in subduction zones. This is where cold oceanic lithosphere is subducted beneath a magmatic arc, and that creates metamorphic conditions that are relatively high pressure and low temperature. And for this to occur, we need the subduction to be relatively fast compared to the speed of heat conduction in rocks. And this means that the rocks can stay cold even though we're burying them deeper inside the earth. So this is this factor of time playing a big part. And the minimum temperatures that we can achieve are limited by the rate of subduction and also by the age of the oceanic crust. The older the crust is, the colder it will be, and the quicker subduction, the further we will be able to bury those cold rocks before they heat up. So that's high P over T metamorphism. We often also refer to medium P over T metamorphism, sometimes referred to as Barrovian metamorphism. That's highlighted in the sort of orange colour there, just below the normal geotherm. And these conditions are typical of the peak pressure temperature conditions in thickened crustal origins, in metamorphic belts like the Himalayas today, or the Alps. And the reason why these are hotter than the normal geotherm is because anywhere where we have thicker continental crust than normal, we will have more radioactivity, because continental crust is relatively enriched in elements like potassium and uranium and thorium, and therefore it's more radioactive than many other types of material on the Earth. And when we thicken the continental crust, we generate more heat by radioactivity, and that allows the temperatures to increase above, or temperatures above the normal geotherm. The temperatures that we can achieve in this tectonic setting is limited by the amount of radioactivity, the heat production rates, so how radioactive the crust is. It also depends on how thick the crust can get. The thicker the crust, the more radioactive material, the higher the temperatures will get. But it also depends on erosion rates. In any part of the world where we get thickened crust, we will usually have high elevation, and that promotes erosion, and therefore the crust won't stay thick, it will erode, it will thin, and that will decrease the amount of radioactive material in that origin. Finally, we have low P over T metamorphism. So these are particularly high temperatures at particularly low pressures, at low depths or shallow depths in the crust. How do we get this? This is commonly a result of what we call advection. We're moving heat by advection. Advection is when heat moves with a rock. The heat itself is not actually flowing from one rock to another. We are moving the rock, and the heat gets carried with that rock. Examples of this would be magmas. So when magmas move through the crust, usually from deep in the crust to shallower levels, they will carry the heat with them, and we call this advection. And this commonly occurs in thickened origins. The other common way that we can move heat is by extension. And when we extend the crust, this brings the mantle much closer to the surface, and the mantle is hotter. So as the mantle moves closer to the surface, it carries its heat with it. So these are two methods of advection. And that's shown here by these arrows on the plot there. What we're doing is we're moving rocks closer to the surface, and as we do that, they bring heat with them, and it allows metamorphism to occur in that low P over T zone in the red. And the maximum temperatures we can achieve in this setting are limited by the temperature of the magma, the volume of the magma. So the more of the hot magma we have, the higher the temperatures will be in the upper crust where they migrate to, and also the amount of extension, which will determine how close the mantle can get to the surface in extension zones. So what we understand is that tectonic and magmatic advection and increased radioactivity can account for most PT conditions that we see in metamorphic rocks. And you can see those shaded fields there. They cover the blue schist facies, the eclogite facies, the green schist, the amphibolite, contact metamorphism. They also extend into the granulite facies. So all of these processes can explain why we get these different metamorphic conditions preserved in rocks. However, there is a type of metamorphism that's much more difficult to explain, and this is at particularly high temperatures and moderate to low pressures, and we call this ultra high temperature metamorphism, and I've labelled it there with the letters UHT. So very high temperatures, relatively low pressures. And although these are quite difficult to explain, these conditions, there's increasing evidence that these conditions have been produced in many metamorphic belts all around the world. So we need to try and find ways to explain how we can generate these conditions. And that's what I'll be talking about for the rest of today. Firstly, what is ultra-high temperature metamorphism? Well, it's been defined as metamorphism that occurs at temperatures above 900 degrees Celsius within the sillimanite stability field. So on that plot there, I've highlighted the aluminosilicate polymorph stabilities. You'll see the, I don't know if you can see my cursor there, but you can see the kyanite field, the andalusite field, and the sillimanite field. Ultra-high temperature metamorphism occurs in the sillimanite field at temperatures above 800 degrees Celsius. Now, actually proving that rocks have been in the ultra-high temperature field is quite difficult. And this is why we are still discovering ultra-high temperature metamorphism today. It's not obvious. And this is for two reasons. Firstly, many rocks do not develop distinctive assemblages in that field. They just look like normal lower temperature granulites. So just looking at the minerals in the rock will not tell us that these reached ultra-high temperatures. The other problem is that many of the minerals re-equilibrate when they cool down. And a very common way of estimating temperatures in metamorphic rocks is to use the mineral chemistry via a method known as geothermometry. And that's based on the chemical composition of coexisting minerals. The problem is at ultra-high temperatures, diffusion rates in minerals are very high. So as the rocks cool down, the chemistry of the minerals reacts and they don't preserve the ultra-high temperature conditions. So proving rocks have got to ultra-high temperature is very difficult. However, there are a few rock types that preserve very distinctive assemblages. And the rock types most commonly used to demonstrate ultra-high temperature metamorphism are rocks that are particularly high in magnesium and aluminium. And these preserve diagnostic mineral assemblages such as sapphirine quartz, coexisting sapphirine quartz, which is shown in the top diagram there. Sapphirine is the bluish mineral adjacent to the quartz. Other rocks might preserve slightly higher pressures and lower temperatures, coexisting orthopyroxene, sillimanite and quartz. At lower pressures, we might get coexisting spinel and quartz, which is shown in the lower diagram. The spinel there is a hersenitic spinel, an iron-rich spinel, a dark green in colour. Also, we sometimes get a rare mineral called a sumalite, which can look very much like quartz or cordierite, or in fact like K feldspar in rocks, and you need to analyse it with the microprobe to demonstrate that it's a sumalite. I should mention that the stability fields of these minerals are dependent on impurities, and just seeing these minerals does not prove ultra-high temperature metamorphism. If you have impurities like ferric iron in sapphirine, or ferric iron or zinc or chromium in spinel, that can extend their stability to much lower temperatures, and you can get these minerals in more normal granulite facies conditions. So just identifying the minerals alone may not be enough. We still need to analyze them and check that they don't contain these impurities that can drop the stability fields to lower temperatures. This shows a phase diagram, the type that's often called a pseudosection, and it shows the stability fields of some of these ultra-high temperatures. So this is drawn for temperatures between about 850 degrees Celsius up to close to 1100 degrees or 10,050 degrees Celsius there, pressures between 6 and 10 kilobars, and you can see the stability field of sapphirine quartz in the top right, and orthopyroxene sillimanite quartz at slightly lower temperatures, and a sumalite at lower pressures. So these are diagnostic minerals that you might find that tell you that the rocks have been to ultra high temperature. Now, the rocks that these occur in, these high magnesium aluminium rocks, are not very widespread. They commonly occur as rare layers and lenses within other rock types. And here's an example from the Rauer group in Prids Bay in Antarctica. It was mentioned earlier that many years ago I did a lot of work in Antarctica in my PhD and a research fellowship just after that. This here shows a very, you can't really see it, but there is a narrow layer of rock that contains sapphire and quartz that runs underneath the hammer in the center of that diagram, but it's only a few centimeters wide. There's more mafic rocks on the left-hand side. There are more standard politic rocks on the right-hand side, garnet and cordierite bearing. So finding the evidence for these ultra-high temperatures can be quite hard. We need to find these layers of high magnesium aluminium rich rocks. However, we commonly assume that the rocks enclosing these layers also experience the ultra-high temperature conditions. They just don't preserve such good evidence for the temperatures. And ultra-high temperature assemblages have now been identified, diagnostic definite ultra-high temperatures at more than 40 locations worldwide. I should say it was more than 40 about 8 years ago when I last gave a talk like this. I'm sure it's more than 50 by now. People are finding these rocks all the time. And the age of the metamorphism ranges all the way from 3,000 million years ago to very recent times. And this map here shows some of these locations. You can see it looks like there are 46 locations on this map. This was from a review paper. I think this was by a paper by David Kelsey. I'm not sure about you, but yes, it is. Published in 2008. And you can see scattered all around the world, some examples in Antarctica at the bottom here, including some examples I have worked on in South America, in northeastern North America, in the Grenville origin and so on, in northern UK, in Scandinavia. There are some examples in the Alps, throughout Russia, in China, throughout Africa, some in Central Australia, and several examples in India, which I will mention in a bit. In fact, I'll mention them now. So ultra-high temperature rocks are particularly widespread in southern and eastern India. Here you can see this map from Fermore's publication in 1936, in which he outlines the basement provinces of peninsular India. And he defined what he called the Charnakitic region. I've highlighted there in the sort of brown colour from the non-Charnakitic region. And Charnakites are rocks that are diagnostic of particularly high temperatures. And we now know, in fact, that throughout that Charnakitic region, there is evidence of ultra-high temperature metamorphism. Assemblages of sapphire and quartz have been found in isolated locations throughout that Charnakitic region. And some of you may have heard of the Fermor line, which is the line defined by Fermor, which separates these very high temperature rocks from the lower temperature rocks in the Darwar Craton and elsewhere. Rather than the Charnakitic region, we now know these as two different terrains, the southern granulite terrain in southernmost India and the Eastern Ghats belt along the eastern margin there. And originally these were assumed to be Archean in age. This was before there was much isotopic dating of the Indian basement. But we now know, in fact, they're not Archean. The metamorphism in both of these areas is actually Proterozoic, but it's different. They're not one terrain, the southern granulite terrain and the eastern Ghats belts, belt have different histories. And the ultra-high temperature metamorphism in these two belts seems to be at different times. In the Eastern Ghats, it's about 1 billion years old, between 1.0 and 0.9 billion years ago. In the southern granulite terrain, 0.6 to 0.5 billion years ago, so about 600 to 500 million years before now. This shows the age of some of these different ultra-high temperature terrains from around the world, and you can see that they stretch back to before 3,000 million years ago, up to very recent ages. And I could just plot on here the age of UHT metamorphism in the Eastern Ghats belt and the southern granulite terrain. And what you note is that the age of this ultra-high temperature metamorphism is not uniformly developed through time. In fact, it's focused predominantly in certain specific time periods. There's a significant number of outcrops that preserve UHT metamorphism in the early Archean. There's another cluster that formed about 2 billion years ago, another cluster about 1 billion years ago, another cluster about 500 million years ago. And we know that these periods in Earth history correspond to the time that supercontinents formed, that the continental crust amalgamated to form a small number of very large continental landmasses. So the Eastern Ghats belt is an origin that formed during the formation of the Rodinia supercontinent. The southern granulite terrain is one of the parts of Earth that preserves the amalgamation of the Gondwana supercontinent. So it looks like the timing of ultra-high temperature metamorphism corresponds often to the time of supercontinent formation. So can we say anything more about ultra-high temperature metamorphism? As I said, it corresponds to periods of continental assembly. Well, in fact, we can look at modern origins that are preserving continental assembly. The best example on Earth is the Himalayas, the Tibetan Plateau, and we can find ultra-high temperature rocks there. They occur as xenoliths in 3 million year old volcanic rocks. So these are xenoliths that are being brought up from deep in the crust beneath the Tibetan Plateau, and these preserve ultra-high temperature metamorphic conditions. So this is suggesting that it's not only ancient origins that produce ultra-high temperature metamorphism, modern origins are also producing these types of pressure temperature condition. So ultra-high temperature metamorphism is occurring today. It's not only a phenomenon of the past. So for the rest of my talk, I want to talk about how we get UHT conditions. It's not easy. And in order to predict it in any quantitative sense, we need to use a little bit of mathematics. I won't be talking much about the maths, but I do just want to show you a very simplified equation. Did someone want to say something?
No, sir. No, sir.
No, sir,
Okay.
Just some noise, sir.
Yeah.
It's fine, sir. It was just some noise. You can continue, sir.
Yeah. No problem. Okay, so I just want to run you through this equation here. This is the one-dimensional heat flow equation. And this is what we can use. I hope you can't hear the background noise there. Someone over the road is making a lot of noise outside my house. So this simple equation here, I can use this to run through some of the main factors that might influence temperatures in the crust and how those temperatures change. I should emphasize it's a simplified equation. It's just considering one-dimensional effects. So all we're considering is depth. We're not considering lateral variations in the crust. We might try to use two-dimensional heat flow equations, which are much more reasonable because we know heat flows laterally as well as vertically. We know that geology varies laterally as well as vertically, but these get much more complicated and they require a lot more assumptions. And I'm just going to keep things simple here today, and we're just going to use the one-dimensional heat flow equation. And what this shows is that how temperature varies in the crust depends primarily on three different factors. So the left-hand side of this equation is how temperature varies with time. And on the right-hand side, we have three different terms that each describe three different mechanisms that can change temperature. And I'm going to go through them one by one. So the first term here is the conduction term. Conduction is how heat commonly flows through solid materials. You'll all be familiar with the concept of conduction. So heat will flow from hot rocks to cold rocks. And the heat flow will be most rapid. The temperature will change most quickly when the temperature difference is greatest. If you have very hot rocks close to very cold rocks, the heat will move very quickly. In other words, the heat will flow quickest when the geotherm is most strongly curved. And that's what this term in the equation is telling us. Also, this factor here, this kappa, is to do with heat conductivity. Some rocks conduct heat more quickly than others. Now, I should mention that this term actually makes it more difficult to produce ultra-high temperature metamorphism because it's telling us how heat will flow away from hot rocks to cold rocks. So this makes it more difficult to get to ultra-high temperature conditions because the heat will keep escaping, it will keep flowing away. So this can't help us explain why we get UHT metamorphism. This actually makes it more difficult. We need to focus on the other two terms of this equation to try and explain UHT conditions. So this middle term here is the advection term. As I said earlier, advection is when heat moves because it's being carried with a rock. The heat itself isn't moving through a material, it's the material that's moving and carrying the heat with it. And the amount of heat change that you get by advection depends firstly on how quickly you are moving the rocks, how quickly you are burying them or exhuming them. The quicker you move the rocks, the quicker the heat will change. It also depends on the geothermal gradient. So in other words, it depends on the temperature where the rock starts, and it depends on the temperature where you're moving that rock to, which we can describe by geothermal gradient. And that's that term in the middle there. And there are two main types of tectonic setting that could cause ultra-high temperature metamorphism. And I've mentioned both of these already. The first one is magmatic advection. We could imagine a situation where a high temperature magma moves from deep in the crust to shallower levels in the crust. And if this magma is much hotter than 900 degrees C, it might cause UHT metamorphism when it reaches the upper crust. Now, to do this, the magma will need to be very hot and dry because that's the only way we can get magmas above 900 degrees Celsius. So in other words, typically very mafic magmas or very, very dry felsic magmas. There's an example here of a very high temperature igneous rock in a ultra high temperature terrain in the photograph here. Again, this is from the Rao group in Antarctica. This is a layered mafic intrusion that would have been at temperatures above 900 degrees Celsius. But if we're going to get regional ultra high temperature conditions produced by these magmas, we need large volumes of these plutons. And we would want to see the timing of the magmatism should be about the same timing as the UHT conditions. So if we date the age of the magmas and we date the age of the metamorphism, we can maybe demonstrate that UHT metamorphism is being produced by magmatic advection. The other type of advection that might cause UHT conditions is extension, in particular extension of the lithosphere. That's shown in this diagram here. A typical geotherm might be running down, it's labelled here as Archean cratonic geotherms, but if we thin the lithosphere and bring the mantle of stenosphere very close to the surface, perhaps to within 50 kilometres of the surface, the geotherm will change to this red line. And you can see that we can get temperatures above 800 degrees Celsius at depths of perhaps only 30-35 kilometres. So we've significantly thinned the lithosphere to bring the mantle much closer to the surface, and we can generate very high temperatures in the crust. The most likely place that we could get this would be in a back arc basin, so immediately behind a magmatic arc, because this is often where we get very thin lithosphere. I can show that in this cross section here. This is a typical cross section of a back arc basin. We have a subduction zone, we have the volcanic arc, and behind that we have the back arc basin where we often have very thin lithosphere, and the asthenosphere can get within 50 or so kilometres of the Earth's surface, and that will generate very high temperatures in the crust. So that's the advection term. The last term for me to go through is at the end here, and this is the heat production term. This describes different mechanisms that can produce new heat within rocks. And this can occur in three ways. We can have chemical heating, mechanical heating, and radioactive heating. So let's just talk a little bit more about those three. Firstly, chemical heating. This is heating by metamorphic reactions. We know that some reactions release heat, exothermic reactions. Some reactions consume heat. They're endothermic reactions. Perhaps we might have reactions that might produce a lot of heat and could therefore produce ultra-high temperature conditions. Well, in fact, this is unlikely because most prograde metamorphic reactions actually consume heat. And particularly as you get close to UHT conditions, rocks will melt, as shown in this photograph here. This shows a migmatite. This shows some, originally this was a turbidite sediment. It's been heated up to temperatures of around 750 degrees Celsius, and it started to melt to produce these migmatite textures. Melting is an endothermic reaction. It consumes heat. You need to add what's called latent heat to the rocks to allow the melting to occur. So this isn't going to help us reach UHT conditions. It's going to make it more difficult because the reactions take in the heat. They don't add heat. We can show this on this plot here. These different curves show the effect of increasing the amount of heat that's consumed in a reaction, increasing the amount of latent heat. And it shows how much it drops the temperature of metamorphism. And we might get 10 degrees C less than we'd expect, 20, 30, maybe even 50 degrees Celsius lower temperatures because of this latent heat effect. So chemical heating inhibits rather than promotes UHT metamorphism. It's not going to help us. What about mechanical heating? This is the heat that's produced in shear zones. So it's produced during deformation deep in the crust. When we deform rocks, that produces heat by friction, and it will depend on the strain rate of the rocks, and it also depends on the strength of the rocks. The more the rocks deform, the more heat they will generate, And the stronger the rocks, the more heat they will generate. Unfortunately, this tends not to help us very much either in terms of generating UHT conditions. So this shows the effect of varying the rock strength. If we want to get rocks to above 800 degrees Celsius, we need rocks that have a strength of more than 30 megapascals. What does this mean? Well, here's a curve of the strength of some typical rocks. At 800 degrees Celsius, many felsic rocks in the blue curve are weaker than that. So at 800 degrees C, they are less than 10 megapascals. In fact, you need mafic rocks to be to generate any significant heat in it. And we know the continental crust is mainly felsic. So it's going to be very difficult to generate mechanical heat in the continental crust by deformation. In fact, the other problem is, even if we have some mafic rocks that might get hot, actually they won't deform very much. It will be the weaker felsic rocks that take up most of the deformation. So mechanical heat won't help us. What about radioactive heating? This is, now I'm getting a message that we might have poor quality. I hope you can still hear me. Radioactive heating is produced by the decay of those 4 elements I've listed on my slide there: potassium, thorium, actually 4 isotopes, and 2 isotopes of uranium. Radioactive heat producing elements are concentrated in the continental crust. We know that. The continental crust is rich in potassium and relatively rich in thorium and uranium. And the amount of heating we get will depend on the concentration of these heat producing elements. And it will also depend on how thick the crust is. So we will get the biggest effect in a thick origin. However, erosion will reduce this effect because it will reduce the thickness. So I'm just going to show you a few calculations. We're going to consider here on the left a normal piece of lithosphere. The crust is around 35 kilometers thick. The lithosphere is about 150 kilometers thick in total. And we're going to thicken that crust. So we're going to double the thickness of crust to 70 kilometers. And then with time, that crust is going to erode back to 35 kilometers. And we're going to calculate the temperatures that we might get. And we're going to vary things like how radioactive the crust is and also how long the crust stays thick. So let's consider a typical origin. A typical heat production of 2 microwatts per meter cubed. That's a typical value for the continental crust. And we're going to consider an erosion rate after thickening of about 0.7 millimeters per year. Again, this is thought to be typical. And we're going to start that erosion 20 million years after the thickening. And we're going to see what happens. Well, these curves here show what happens. The red curve is where the geotherm starts. Then we thicken the crust. Initially, that actually lowers the geotherm to this blue curve at the left. And then the radioactivity heats the rocks up, and we get these colored curves moving progressively to the right. But you can see none of those curves ever reach ultra-high temperature metamorphic conditions. Why is this? It's because erosion starts to thin the crust again, and the radioactivity never gets to build up because the crust thins, the material gets eroded and transported elsewhere. And the maximum temperatures we can generate in the middle crust here is around 600 to 700 degrees Celsius. We don't get to 900. So what can we do? How can we get to our ultra-high temperature conditions? Well, the first thing we might do is increase the amount of heat production. And that's what this these curves here show. These show the effect of making the crust more radioactive. The green curve is the value we chose before. That's a typical value of about 2 microwatts per meter cubed. To get to 900 degrees C, we need radioactive concentrations or heat production amounts of at least 3.5 microwatts per meter cubed to get to ultra high temperatures. Now, we do get some rock types that can be they can have that level of heat production, but not across a whole origin, not the entire crust. So this won't really help us. We might have some layers with that value, but it will be very, very difficult to imagine an entire crustal section that had heat production levels that high. The other thing we might do is reduce the erosion rates, because, as I've said, its erosion stops the radioactivity generating that heat. So this plot here shows what happens if we vary the erosion rate. Again, the green curve is the typical erosion rate that we used before, of about 0.7 millimeters per year. And you can see under those conditions, this shows that the time after thickening, temperatures get to about 600 degrees C with an erosion rate of 0.7, and then they drop off. The red curve and the blue curve shows what happens if we reduce the erosion rate. And what you can see is that to get temperatures above 800 degrees C and approaching 900 degrees C, we need an erosion rate that's as low as 0.05 millimeters per year. If we can make the erosion that slow, then that gives the thickened crust enough time for radioactivity to have an effect and for the temperatures to build up. If the heat production was higher, we'd need less time. If the heat production was lower, we'd need more time. So can we think of a place where we have a thickened origin, but the erosion rates are really low? In fact, there are some places on Earth where this is the case. And this is an orogenic plateau like Tibet. So Tibet we have very thick crust. We have high elevation. It's about 5,000 meters above sea level. And the crust across the Tibetan plateau exceeds 70 kilometers thick. It's more than 2,000 kilometers wide, which also helps limit the heat loss. But the critical point is that the erosion rates on the plateau itself are very low. At the orogenic front in the Himalayas, where the mountains are, erosion rates are very high, and they're more than 1 millimeter per year, as you would expect, where you have a lot of topography. But in the plateau, the Tibetan plateau behind the mountains, the erosion rates are very, very low. In fact, they're less than 0.01 millimeters per year, even though the crust is very, very thick. So this suggests, our calculations suggest, that erosion is slow enough in that piece of thickened crust that we could be generating UHT conditions within the Tibetan plateau. And that's actually what we find. I mentioned before those xenoliths that are found in the relatively recent volcanic rocks on the Tibetan plateau. These volcanic rocks are bringing up UHT materials. So we know that ultra-high temperatures are being generated beneath the Tibetan plateau. Why is that? Because we have thick crust, but also very low erosion rates. So what this suggests is that with time, if the Tibetan plateau is eroded, we will probably find ultra-high temperature rocks. And then to its north, India will have a northern granulite terrain to act as a counterpart to the southern granulite terrain that is already exposed in very southernmost India. So I would predict that there is an ultra-high temperature granulite terrain beneath Tibet. So to conclude, how does the crust get really hot? How do we generate these ultra high temperature metamorphic conditions? Well, there are three settings most likely to generate ultra high temperatures. Regions with abundant, hot, dry magmatism. So in these areas, we'd expect to see a lot of very high temperature plutons. Another place we might generate these conditions is in a back arc basin, where it's being driven by advection of the mantle. So the lithosphere is very thin. That brings the mantle very close to the surface. We get very high temperatures. And the third setting is a long-lived orogenic plateau. All of these three situations are likely to generate ultra-high temperature conditions. If I just consider now the two areas of ultra-high temperature metamorphism in India, these two photographs here on the right are from the Eastern Ghats belt. And I'm going to suggest that perhaps at least part of the UHT conditions here are generated by magmas. If it's generated by magmas or in a back arc setting, we would expect to see lots of evidence for magmatic rocks. We see this in the Eastern Ghats. There are a lot of very high temperature charnockite magmas in the Eastern Ghats. We'd expect to see evidence of a greater mantle influence. So we would expect magmatic rocks that are more mafic or are more juvenile, evidence of not having been extracted from the mantle for very long periods of time. We'd expect the ultra-high temperatures to decay pretty soon after the magmatism or the extension has stopped, and we would expect to see pressure temperature paths in those metamorphic rocks dominated by heating and by cooling, perhaps with relatively limited changes in pressure. So they're the things we should look for if our ultra-high temperature metamorphism is to be produced by advection, by magmatic, by high temperature dry magmas, or by extension in a back arc setting. The second possibility, a long-lived orogenic plateau, I would suggest that the southern granulite terrain is a typical example of this. The two photographs here are from the southern granulite terrain. The top one shows what's commonly referred to as a condylite in the southern granulites. So we have a cordierite sillimanite bearing rock there. The rock below that is that's more of a charnockite with orthopyroxene. But in this case, it's probably not a magmatic charnockite. It's an incipient charnockite that's formed within a sedimentary or volcanic sequence. So in areas where the UHT has been produced within an orogenic plateau, we would expect any magmas to be produced locally by melting, not by addition from the mantle. So we'd expect a greater continental influence in these origins. We'd expect to see evidence for heating over a very long time to generate the ultra-high temperature conditions. It takes maybe 70 million years for the radioactivity to build up long enough to generate those UHT conditions. We'd expect the ultra-high temperatures to continue as long as the plateau remains thick, and then the end of the ultra-high temperature conditions will occur when the plateau collapses. And when this occurs, we would expect to see pressure temperature paths dominated by pressure change, by decompression. And what I would like to do is finish there. So those two different examples of ultra-high temperature, the Eastern Ghats belt and the southern granulite terrain.
Thank you, sir. I would like to thank Professor Fitzsimmons for this wonderful session. Thank you, sir, for sharing such enriching knowledge with us. We have received several questions from our audience which are in the process of being compiled. Once done, we'll surely like to address the questions. In the meanwhile, I'd like to remind everyone that today we have another lecture scheduled at 4:30 p.m. Indian Standard Time, which is going to be delivered by Professor Pulak Sengupta, Department of Geology, Jadavpur University, on the topic Marvelous Marbles from Sight to Insight. We are really overwhelmed by all your response to our endeavors, and so far we would even more happy by your presence in our next lecture session. Please wait just a few more moments and then we'll start with our question answer session. We have our questions now. Please note that owing to the large number of questions that we have received and also due to the time constraint, it will not be possible for the speaker to address all of them. However, we shall try to take as many as possible to the speaker within the stipulated time. Sir, shall I start with the questions?
Yes, please.
Okay. So the first question is from Mr. Priyanjan Datta, research scholar, ISER Bhopal. He asked, what UHT assemblage can we expect for a low aluminium bulk composition rock, for example, say dunite?
Ah, that's a good question. So it was a dunite, did he say?
Yes, sir.
A dunite. So, well, obviously a dunite is a rock that's made up almost entirely of olivine. And if it is made up almost entirely of olivine, I would expect it still to be olivine at ultra-high temperature conditions. Because we know that olivine is stable under high temperatures, because that is what we see in the mantle in peridotites. However, it would be very unlikely in an ultra-high temperature terrain to preserve that olivine, because when those rocks come to the surface, they will retrogress. So I think a dunite, we're actually very unlikely to see the ultra-high temperature assemblage preserved. It is far more likely to be overprinted as the rocks come close to the surface, and it will become a much lower temperature rock, like a serpentinite, because dunites are so reactive as they undergo retrograde metamorphism.
I hope that answers the question. The next question is from Devarun Mukherjee, who is a student of UG3 of Presidency University. He asks, instead of constraining the individual boundary parameters for the models to explain UHT, is it possible to vary the combination of the boundary parameters of the factoring variables to explain the UHT observations?
Right. I'm not completely sure I understand exactly what the question was. Can you just repeat it?
Yes, sir. He is saying instead of constraining the individual boundary parameters for the models to explain UHT, is it possible to vary the combination of the boundary parameters of the factoring variables?
Okay. So if I understand it correctly, and I should say I am not a numerical modeler, that's not my expertise. I think what the question is saying is in my talk, I considered each of the variables one by one. So I considered the effect of changing the erosion rate. Then I considered the effect of changing the heat production. And I think what the question is saying, what happens if you combine different variables at once rather than considering them one at a time?
Yes, sir. I think that's
Yes. Now that obviously gets very difficult to explain because there are many combinations. But yes, all of these things can operate at once. If you have a higher heat production and a lower erosion rate, then it becomes easier to get ultra high temperature conditions. If you have increased strain, that would add to the mechanical heat. All of these things can operate at once. It just becomes very difficult to show what is happening in any simple way because there are too many variables. And I should say, because these are one-dimensional models, that they're very simplistic anyway. To be more accurate, we should consider two-dimensional models that allow for heat to escape or move sideways, and also allow for different rock types adjacent to other rocks. But yeah, it's a very good question. It just becomes far more difficult to describe and to explain.
Okay. The next question is from Mr. Shubham Datta, PG student, IIT Kanpur. In a partial melting scenario in UHT metamorphic condition, to what extent the signatures of back reaction between the melt and ambient rock are decideful or significant?
Okay. So the question was to do with back reaction of rocks after they melt. This certainly has some effect. As what it will do, I imagine, is slow down the cooling. So as I said, we need to consider chemical heating as a factor that changes temperatures. And during prograde metamorphism, as we melt rocks, that tends to slow heating down because we need to add latent heat to the rocks to produce the melt. The opposite will occur as rocks cool down, and back reaction will tend to liberate heat. It's the opposite of the heat that's consumed as we produce the melt. As the melt crystallizes, it will release heat. So it will extend the period of high temperature metamorphism. However, it won't help us reach UHT conditions because melts will generally crystallize at temperatures below UHT. So we'll already have dropped below 900 degrees C when the back reaction occurs. But it will certainly mean the rocks remain in more normal granulite to upper amphibolite conditions for longer. I hope that answers at least in part the question.
The next question is from Orchishman Chaudhary, who is a UG3 student at Presidency University. He asks why the UHT metamorphic outcrops are found around the Dharwar Craton in India. Why not in the craton exactly, although the entire craton has undergone metamorphism under a rift basin setting? It is more likely to get UHT outcrops in the exact Dharwar Craton.
That's a good question. So I am not sure whether anyone has identified ultra high temperature metamorphism in the Dharwar. I have a feeling that there might have been some recent discoveries, but I am not fully up to date with the literature. But it is certainly true that it is much more common in the orogenic belts around the Dharwar. So within the southern granulite terrain to the south, within the eastern Ghats to the east. The reasons for that are, it's a very good question. I think it's because one possible reason is that the crust in the Dharwar did not get so thick. So it was not a thick plateau. So we couldn't generate the extra heat by radioactivity. There is magmatism in the Darwar craton, of course, but perhaps the magmatism was not so hot, so it was not 900 degrees Celsius or more magmatism. It was lower temperature magmatism. And yes, there is certainly evidence of back arc conditions that there are models that suggest the Yilgarn, sorry, not the Yilgarn, the Darwar craton. I'm mixing up with Western Australia. People have certainly suggested that these Archean cratons, that there's evidence for back arc processes and for arc terrains. But perhaps the lithosphere was not able to get so thin. I'm not an expert on the Darwar craton, so I can't really say much more.
Okay, sir. The next question is from Mr. Shiv Narayan Das, research scholar, Delhi University. He's asking, according to you, we need low erosion rates and thicker crust setting for UHT metamorphism. But in continental assembly stages and back arc settings, none of the above might happen. How can you explain this?
Okay, the first point I'll say is that forming UHT rocks in an orogenic plateau is only one method to produce ultra-high temperature rocks, and you can also produce them in back arc settings, but they are two different drivers for the high temperature orogenic plateau. The main cause of the temperature is radioactivity. And if you want to achieve UHT conditions by radioactivity, you have to keep the crust thick for a long time. So you need a plateau. You can also produce UHT conditions in a back arc basin, but that is not, the heating there is not due to radioactivity. It is due to the mantle getting closer to the surface and bringing heat with it. So that is mantle advection. Both are possible. So some of the UHT rocks that are produced during periods of continental assembly might well be produced in back arc basins in areas of thin lithosphere. That's certainly possible. Others might form in orogenic plateaus. Yeah. So I'm not saying that you have to have thick crust and low erosion to produce ultra high temperatures. I'm saying that is one method. The other method is to do it in say, back arc basins where you have mantle advection. So both are possible.
The next question is from Dr. Shreya Kormakar, postdoctoral researcher, Department of Geological Sciences, Jadavpur University. She's asking, regarding UHT metamorphism by advective heat transport, is it possible for a magma with a 900 degrees Celsius heat to 900 degrees Celsius to heat surrounding rocks to UHT conditions?
No, not if it's only 900. So we take our definition of ultra high temperature metamorphism is 900 degrees Celsius. That's sort of an arbitrary number, but if we take that number, then the magma really needs to be hotter than 900, or else it is never going to heat the rocks adjacent to it to 900 degrees Celsius. So if our magma is 900 degrees C, only the rocks very, very close to that magma will ever reach 900 degrees C. So we won't see it. To produce UHT conditions in the country rocks, we need the magma to be hotter than 900 degrees C to be able to see those conditions in the adjacent rocks. And the hotter the magma is, the more likely we are to see those conditions.
The next question is from Mr. Rahul Sen, PG student, Jadavpur University. He's asking, was the southern granulite terrain of India once upon a time thick like the Tibetan plateau?
I think Yes, I would say certainly the area I've worked most on in India, which is the southern granulite terrain. I believe that about, say, 550 million years ago, the southern granulite terrain was just like Tibet. It was an orogenic plateau. It formed during the assembly of Gondwana, so just as the Tibetan plateau formed after the collision of India with Asia, I believe the southern granulites formed during a similar collision that produced the Gondwana supercontinent. And then after erosion of that plateau, we see the granulites that are the southern granulite terrain.
Okay. The next question is from Dr. Shudipta Topon Sinha, professional employee, Reliance Industries, India. He's asking what effects we should expect in the chemical character of the sediments which have UHT terrains as a provenance.
That's. Can you just repeat the beginning of the question? Which characteristics?
He's asking what effects we should expect in the chemical character of the sediments.
Right, yes, the chemical character. I'm not sure that it would be possible to use the simple chemistry of the sediments to demonstrate that they've been eroded from an ultra high temperature terrain. You would probably need to look at the chemistry of the individual minerals. Perhaps the trace element chemistry of the individual mineral grains, like the zircon grains, might preserve certain signatures that they formed under high temperatures. But I would not expect the bulk chemistry of the rock to really show much difference. It could, if the ultra high temperatures were produced by magmatic advection, so by mantle influence, you might expect to see a more mafic composition in the sediments. But if it's an orogenic plateau, the rocks are continental, crustal in origin. They would not be so different, I don't think, from a non-UHT origin. Perhaps they'd be slightly less felsic because they're likely to have undergone higher degrees of metamorphism and therefore partial melting, and perhaps they would be more residual because they'd lost their partial melts. But I think it would be very difficult to see a significant difference in the chemistry of the sediments. Yeah.
The next question is from Miss Simran Datta, PG student, University of Calcutta. She's asking, in case of the Tibetan plateau, does the volcanic melt react with the UHT rocks?
Can you repeat that again? Sorry.
In case of the Tibetan plateau, does the volcanic melt react with the UHT rocks?
Excellent question. So this would be the xenoliths that I mentioned. Now, I haven't studied those rocks. I would need to read the original paper. It was a paper by Brad Hacker, in particular, that was published in Science. It would be really interesting to look at those rocks. I wouldn't expect much reaction because the UHT rocks would already have high temperature minerals. So you would expect them to be quite stable in the high temperature magma. So there might not be much reaction with the host magma, but I don't know for sure. But that's a really good question, and it's got me interested. I might go and read the paper again when we finished here today.
Okay. So the next question is from Mr. Manavendra Kuiri, PG student from the IIT Bombay. He's asking, as the whole term associated with the kappa in the equation decreases the chance of formation of UHT condition, then why is it not made negative?
Okay, that's a good question. I'm going to need to look at the equation again. That's a very good question. I'd need to go back to the equation to be sure, to give a definite answer. But the reason it's that equation, on the left-hand side, it was the change in temperature with time. And it was a positive, so that kappa would normally be a positive value because it's the conductivity. The higher the conductivity of the rock, the more the temperature will change with time. Whether it increases or decreases depends on where you are in the crust, but that equation considers both heating and cooling. I'd need to sit down and think about that question with the equation. It's a good question. I'd need to think more about it. Sorry.
Okay, sir. The next question is from Mr. Dibbendu Sarkar, who is a PG2 student at Presidency University. He's asking, we can see most of the UHT metamorphism had occurred at the time of supercontinent cycle, but few also occurred in the span between the two supercontinent cycles. What could be the cause of that?
That's a very good question. Perhaps they could be examples where the UHT was produced in a back arc basin, because we know that there are at any time in Earth history, at least in maybe not in the very beginning of Earth before plate tectonics, but for much of Earth history, there are always subduction zones somewhere. And if there are always subduction zones somewhere, that there will be magmatic arcs and there will be back arcs. So perhaps some of those examples are during ongoing subduction in a back arc, not during the times when we're getting the collisions during supercontinent assembly.
Okay. The next question is from Dr. Somesh Chatterjee. He's a faculty at the University of California, San Francisco. He's asking, what can you say about the stability field of the UHT metamorphism in case of advective transport when the PT conditions exceed the limit of 900 degrees?
Okay, you're going to have to repeat the beginning again for me.
Yes, sir.
Sorry.
He's asking, what can you say about the stability field of the UHT metamorphism in case of advective transport when the PT conditions exceed the limit of 900 degrees?
Okay, the stability fields of the minerals do not really, they don't depend on the mechanism for the heating. So it does not really matter whether it's advective heat or conductive heat. They're just showing the stability of the minerals for certain pressures and temperatures. So I'm not really sure I completely understand the question. I might have to leave that one.
Okay. We are getting a lot of questions, but I think due to the time constraint, this is going to be the last question we'll be taking today. So this is from Dr. Anto Francis. He's the faculty at the Government Engineering College, Thrissur, Kerala. He's asking, Can a short-lived collision origin produce UHT when it collapses by tectonic thinning?
Yes. In theory, so if it's during the collapse, during thinning, it would not be radioactivity that's producing the heat because you have thin crust. But if the collapse was very dramatic and you thinned the lithosphere substantially and you brought the mantle up close to the surface, then you could generate ultra-high temperatures in the crust, but it would have to be very significant collapse. So essentially you'd be creating conditions like just like a back arc basin, but it is possible, and certainly people have in the past suggested that you can get very extreme ultra-high temperatures during the collapse of an orogenic belt. And what you would look for there is the timing of the high temperatures. In that case, the ultra-high temperatures should be reached during and after the decompression of the metamorphic rocks. In the model I talked about in the orogenic plateau, you would expect the high temperatures to be produced before the decompression. But yes, it is certainly possible.
Thank you, sir. Thank you for again taking all the questions. Though there are still a lot of questions left, and we are really sorry that we won't have enough time to address all of them. But we will be surely sending them to Professor Fitzsimmons. So rest assured. Okay, now I would like to call Debarati Shah to deliver the vote of thanks.
Thank you, Shinyon. On behalf of the Geological Institute, I extend a really hearty thanks to Professor Ian Fitzsimmons, who spared time from his busy schedule to be with us today. We have had the great opportunity to hear his thoughts, and this will surely encourage us in our future endeavors. Once again, thank you so much, sir. We are eager to maintain this relationship of love amongst us, and we hope to have you with us in the future for any such lecture or workshop. Please visit the Department of Geology Presidency University if you happen to find yourself in Kolkata. Now, I would request everyone to turn on their camera so that we could take a screenshot to make this event a memorable one. Please keep your microphones off. It's done, sir. Thank you so much. Hope to see you all again as we reconvene at 4:30 p.m. Indian Standard Time. Till then, adieu and have a nice day.
Thank you very much, everyone, and thank you for all of your questions. I have not had to think so hard for a long time, and I will do my best to answer any questions that I'm sent after the talk. So thank you, and I have visited Kolkata once, but next time I visit, I will have to visit the Presidency University. Thank you.
Yes, sir, sure, sir.
Thank you. Thank you, Yali, for this wonderful lecture. Thank you.
Thank you very much.